Okay, so first things off, a couple of things off the top. So this current homework assignment, which is due, next week? I forget the date. Let's look. I believe it's the 21st, but I don't want to say that and be wrong. Yeah, so it's due on the 21st, which is the end of next week. So what I will probably do early in the week next week, I would say maybe tomorrow, but for sure early in the week, I'll post kind of a 5th homework assignment, and it'll be optional in the sense that I'll only use 4 of the 5, right? So if you've already done the first 4 and you're okay with that, you don't have to do the 5th one and it won't count, right? I'll drop kind of the lowest. If you had an assignment you didn't do too well on, kind of that 5th one would be a way to try to improve that score, right? To replace one of the first 4 existing ones. So obviously that 5th assignment is going to have a due date that gets pretty close to the final. And so I don't want anyone to feel like they have to do it, which is why I'm kind of making it this way where it's like a replacement assignment or if you've done the first 4, you don't have to do the 5th one.
Will we get to know our grade for homework 4 before that?
Well, so that's the thing. They'll be kind of overlapping. I'll try to get those 4 assignments graded as quick as possible, kind of after that due date. If you turn them in early, I could potentially, grade them kind of prior to that due date and let you know what you get. That way you can kind of make your choice on that 5th one. But my suggestion would be try to do that 4th one. I'll probably make the 5th one a little bit tougher. It'll probably have some more stuff that are related to linear regression, because that's what we're going to be kind of more focusing on kind of the last couple of weeks, is really going through papers. Not a lot of new topics, some new topics, but primarily trying to understand those topics through work that's been done. Okay. Any other questions on that before I keep going here? Okay. The next thing, I've had a couple people kind of mention this, and honestly, I don't know how much grading I'll be able to do that weekend. So I'm going to change the due date on I'll post kind of the project so you can start uploading those if you're kind of completing them. I had a couple people who I've talked to are pretty much done. So for those of you who aren't, I'm going to extend the date of that project. I think it was supposed to be next Friday. I'll kind of push that out to be the end of the weekend. So the end of the day, Sunday. So you have a couple extra days and kind of that weekend to finish that up. And other than that, I think that's all I want. Oh, homework, also on homework 4, that first question. So we'll just open it up here. I have a slight typo in it, so it'll make it actually a little bit easier. I meant for 1A to be what would happen if the discrimination was coming from small market teams. It says large market, but it also says large market in C as well. So A and C will really primarily be the same question, with a couple more, a little bit more detail in C than in A. And that's because I thought I was writing A for if the small market teams were discriminating. So you kind of are answering the same question here in 1A and C. Okay. All right. Any other questions from me before we get going here? Yeah.
I guess for the project, do you have any example projects on there?
Yeah, so there should be one. Oh, I closed the web browser. So if we go to files, you go to course project. So there's an example project up there. So this was one that was actually done, and is probably the best one I've seen up to this point, which is why I use it. And then kind of a little bit more description of the project opponents. And then this, hopefully at this point, project ideas shouldn't be a relevant file at this point. Okay. Any other questions? All right, so one thing for the project that I have had a couple people ask a similar question is, we're thinking about the literature review portion. So where is it at? Here we go. So I think this paper's got 1, 2, really primarily only 2, right? So when I said multiple, right, 2 or more is what I'm looking for there. Now, if you're using 2, this is a good example project because there's a pretty detailed write-up and summary of those 2 papers, like pretty lengthy paragraphs. I don't want you just to kind of mention in a sentence 1 or 2, right? You're trying to describe or kind of provide a summary of what these other, research papers or articles or whatever the sources kind of found, okay? but yeah, at least 2 there. If you want to do more, you can do more. That's always good, but kind of at least 2 being the minimum there. Okay. Any other questions? We keep pushing here. So today might be a little bit short of a class. We're going to jump around a little bit. I'm going to show you some things, kind of the last, kind of finish out this amateurism and then kind of dive into a couple papers and show you some stuff in Excel as well. So we left off last class thinking about kind of this expected kind of, salary of going, starting from high school, playing different sports. So some other issues that we might have, or we have currently that revolves around NCAA college athletics is a decision of whether or not a player should stay kind of in college sports or leave for the pros, right, if they're good enough. So obviously a lot of things that would matter here are the quality of the player, right? If we're thinking about the higher the quality, the higher the expected money, and then they go to that professional level. Maybe thinking about the quality of the team that they return to. So if they stay another year, will that team have success, and will that increase the probability that potentially they look better for the professional teams? A preference for education, right? If there's just a strong, depending on what their major is, kind of what's their outside option, how much money could they make with that degree? And then quality of the current draft class, right? So here we've got kind of this, you could probably model this in a normal form game where you think about if the current draft class is really high quality players, so you're going to be competing with other high quality players to get drafted highly, then potentially you would want to wait around a year if you think that the next year's draft class is going to be a little bit weaker, kind of making your relative performance a little bit better. Right? So these are things, we could model. It would be kind of difficult, so we won't dive into like the model itself. It was probably outside the scope of this class to incorporate all these things, but we can at least think about the aspects that would matter. Right? So if we're trying to model this value of staying versus returning, we'd really be thinking about utility, not only the money they could make at the professional level, but right, some utility potentially of having, obtaining their college degree, maybe if they're the first in their family, or, it's just been always something they wanted to do. That would all kind of play a role, right? So if we're looking at kind of this idea of leaving for the pros, there's an interesting idea about can we somehow estimate what colleges should be paying players based off of how much revenue they're generating, right? So what we could try to do is estimate the effect each additional player has, so each player that's drafted to the NBA, how much revenue were they generating on their college team, right? If we could somehow figure out the additional revenue that player was generating, or the value of that player's marginal product, or the value of the marginal wins that come from that labor, right? Then that would give us an idea about what that player should be paid, right? In a free and open labor market, they should be paid exactly the value that the revenue they generate. So if we had an idea about the distribution of NBA salaries, and then we use kind of the marginal revenue that comes from the product, or the marginal wins, the value of the marginal wins that come from that labor for the star players, we could then kind of scale it. All right, so we could look at the distribution we see in NBA salaries, kind of overlay that onto NCAA players, right? So what we're finally going to do is then look at, okay, what percent of players, right, are going to be making above or below their scholarship amounts. Okay? So there's a paper that did this, and essentially what we're trying to get at here, this kind of introduces some linear regression stuff. Dot cam catches up to us here. All right, there we go. This kind of looks, hopefully that looks a little better. So you can think about one thing that we could estimate, right, is the impact on wins, right, that come from all these different performance measures. So maybe this is like points scored in a season from a player. Maybe this is, rebounds, all these different statistics, right? And look and see at how each player, if they have a high number of points, and we would also want to control for things like teammates' points and things like that, right? But once we've run this regression, essentially, if we have all these performance measures, we can look at, well, what is the predicted increase in wins that would come from that? Once we have these estimates, all these coefficients, for any one player, we might have a line of data where it looks like this, right? So points, rebounds, all these other variables. And maybe for player one, right, we see that they average 20 points a game, I don't know, 7 rebounds, assists, all this stuff. Well, for that one player, we now have values for every one of these variables. We also have the coefficients. So if we were to plug in that player's performance statistics after we ran this regression across all players, then we could come up with a predicted number of wins that that player is adding, okay? So we could essentially run this regression, obtain these coefficients. Here's the impact on the number of wins from, a player scoring 1 additional point per game. Well, if that player scores on average 20 points per game, the increase in predicted wins would be 20 times whatever that coefficient is. But we have all these other factors as well that we know are going to help increase or decrease wins. Some could decrease, like, maybe we have turnovers over here. And so if I'm thinking about, I just wrote multiple B4s. This was B3. Maybe this is actually negative for some variables, right? But we could come up with a predicted number of wins that each player is adding. Well, what would that prediction be? It's essentially the marginal number of wins that come from that player's labor, right? So if we're thinking about the demand curve, we know that the demand curve for labor is composed of 2 things. For every player, we now have kind of come up with a predicted number of additional wins that they would add. And then the marginal revenue per win, right? That's going to come by looking at kind of the, you could almost think about if we had revenues for all these different basketball or NCAA programs. If I think specifically the paper we're going to look at is basketball. Well, I could look at the revenue generated from that team, right? And I think a couple of you, I think, are using it for your project. And I believe I showed you some, when we look at the subsidy data, we had some idea about what total revenues were. If we look at total revenues and divide it by the number of wins, we could come up with the marginal revenue per win, right? Kind of treating it linear there, but we could still do that. Well, once we have those 2 things, that's essentially what they were kind of getting at here was, these players that were drafted from large schools, what was the impact on their team's revenues? So they looked at players that ended up leaving college basketball, and they did it for non-large schools as well. There's no significant effect there, but for these large schools, there was. Right? So you can get an idea about how much these players were adding in terms of additional revenue. You could then, multiply marginal revenue per win by the marginal kind of wins coming from each one of those players and get estimates for what kind of the median kind of value of the marginal. So this is the marginal revenue that comes from the production of the players. We can think about this as really when we have been thinking about this value, what we've been calling that is the value of the additional wins that labor adds, right? So we could calculate those values. So that's what this paper does, right? And they do it for low and high revenue schools. And there was 3 different kind of approaches. You can kind of see the values range, or there's a decent range to these values. The paper specifically I pulled the rest of the tables from was this Brown paper. They kind of don't, they had kind of the middle of the road valuation of the 3 for high revenue schools and kind of the highest for these low revenue. But if we use Brown's values, and then we can kind of compare it to what the athletic scholarship values are, we kind of notice that the percent of players who would, should be getting paid more, right, than what the athletic scholarship amounts are. And these are kind of, they use 3 different kind of threshold cutoff points. We kind of see that about 60% of players have or bring value to the team that's above that tuition remission, or what, everything that involves, right? Room and board and these things like that. So about 60% of student athletes are underpaid when it comes to, and college basketball. I believe this was specifically looking at NCAA basketball. It is a similar thing for football as well. I think there they found a slightly fewer players are underpaid. I think it kind of depends on the position you look at there. But this is kind of interesting finding where we can start to think about, well, look, we've got really just 2 components that we need to understand to determine what the value of that player is to the team. One is the marginal revenue that comes from each win on that team, which we can gather data on revenues and the number of wins for each program. And we can estimate this number of additional wins that the labor is bringing in by using a regression equation like this. Okay? It's a little bit complex. We're kind of getting towards the end of the class. So I'm starting to show you a couple things that, it's not like I'm going to expect you potentially to do this, although in some of your projects you could. Like I remember, I think a couple of you actually chose this topic, so I'm helping you out a little bit. But there was someone trying to, I had someone do a project where it was like, they were looking at fourth downs, so successful fourth down, and then looking at like all the different things. So like, the yard line that they were on, all these different kind of things that would influence whether or not, right? It's a 1 or a 0. 1 if you are successful on a fourth down attempt, 0 if not. Once they had all these coefficients, they then estimated what the likelihood was for every single fourth down that occurred. They could plug in the scenario of that fourth down, all these different variables, along with these coefficient estimates, and predict, what the likelihood was that they were successful on that fourth down. Right? So you could do things like that, and I'll show you a couple things once we get to Excel as well that will kind of relate to this idea. Okay. Any questions on this before we kind of move on to the next? Shouldn't be too bad. So the next thing I want to go over is a paper which looks at player performance and long-term contracts, right? So I've got some slides. We'll probably switch over to the paper at some point, but I try to kind of grab the most important points. So basically the question of the paper, and I think it's Stroh is his last name, Kevin Stroh maybe, is do players perform worse after signing a long-term high guaranteed kind of contract or have high, long-term guaranteed salary? So the idea that if I'm, have this long-term contract and a lot of it was, guaranteed money, maybe I can coast a little bit now, right? There's not this, there's a little bit of a, my incentives are gone, right? Because I'm going to get this money no matter what my performance is now that I've signed this big long-term contract. Like Patrick Mahomes, right? He's got next 10 years, he could, end up being the worst quarterback in the league, and he's still going to be getting paid a lot of money. So the paper went out. It grabbed some data, about 10 years of data on Major League Baseball, right? And uses this metric, which is called WAR, which is wins above replacement, right? So this is like the number of additional wins that a player brings in above like an average replacement player. So like above the average player in the league. So this is supposed to capture like player quality without needing like 50 different performance metrics, right? I don't need to know the home runs, doubles, strikeouts, walks. I can build that all into one statistic, okay? So I think that's what they used for position players and pitchers. And then they used the OPS, which this is what, not on base plus slugging, I think. Yeah, I was gonna say, sometimes I have a hard time remembering these abbreviations, but on base plus slugging, which is supposed to kind of capture, how often are they in chances to score and how often are they allowing other players to score by like getting a hit or something that drives that player in. Okay. So we've got measures, singular measures of performance. What they then do is say, okay, look, I'm going to look at the performance of the player using this metric of like WAR or their OPS, right? Depending on, run 2 regressions here. But for the sake of discussion, we'll just say that they're using that WAR, that wins above replacement variable. So in the current year T, what was the player's performance? What was their WAR metric? Okay. We'll then add in all these additional control variables, which is kind of what their age is, their age squared, how many plate appearances they get that year. And then we'll kind of look at what their performance was in the 3 years prior. Okay. So these 3 years prior should be a good predictor of what their performance will be in the following year. So we could do that and say, if they perform better this year, here's what their performance, predict what their performance should be, right? Same kind of idea. I run this regression. I get estimates for each one of these beta coefficients. And then for every player, I look at what their performance was, multiply that by the coefficients, look at what their age was, multiply by those, add them all together, and I can get this predicted performance. So I know how they should be performing that year after they sign a contract. So what we're then going to look at is once I have this predicted expected performance, right? I'm predicting what their performance should be. We'll call this kind of their, their expected performance minus how they actually perform, their kind of shirk value, right? Essentially, they were predicted to perform at a certain level, and if they didn't quite meet up to that, the WAR was lower, then we'll get this kind of positive difference, right? That they actually were kind of not, that they weren't performing up to the expectation, and vice versa if they performed, not productive, performed. So we can look at the effect that this contract length or value will have on this shirk value, this difference between expected and actual performance. So we'll look at that shirk value, right? The predicted minus the actual performance, and see that the contract length, right, is going to be, and the contract value, or what we think are probably going to influence this, right? If I sign a larger contract and it's a longer contract, we would expect these coefficients to be positive, right? That if I sign a longer contract, that there's just less of an incentive for me to try hard. And so when I look at that shirk value, that expected performance is probably going to be above what the actual performance is, because I now don't have this incentive to like play really well so I can get a big contract. So we think these will probably have positive kind of coefficients here. Right? So the authors kind of break up length into this dummy variable, which is, do I sign a 1-year contract, a 2-year contract, a 3-year? And if it's a 1-year contract, that variable takes on a 1. If it wasn't a 1-year contract, it takes on a 0. Right? So we have all these indicators for the different lengths. So here, we've got 2-year contracts all the way to 10-year. Now, the one that they left out was a 1-year contract. This is kind of like, we have to have a comparison group. So anytime we want to include these indicator variables, well, we have to have a comparison group. The comparison group here would be which one we left out, which is just a regular 1-year contract. Because we can kind of think about that should be like the worst contract you could sign in terms of, and I shouldn't say worst, the contract that you could sign that you would still have to then play for your next contract, right? So they did this 2 ways. We'll focus kind of on this first column first. So here they didn't break it down into different years. They just allowed that the longer the contract was, what was the impact it had on shirk value, right? And the value of the contract, what was the impact? Well, here, this lines up with what we were expecting. Holding the length of a contract constant, if you give that player a higher valuation, the shirk value we see actually increases, right? So the difference between the expected and actual performance got wider, right? Or I was underperforming, okay? So this is, evidence that larger contracts, right? The player now feels set, maybe they, kind of this income effect, their supply curve of labor shifts. And so they don't try as hard and their actual performance starts to get further below the expected performance, or that shirk value gets larger, right? That's why we see this positive effect here. All right, so we're going back here, we found a positive coefficient. The contract length is interesting because it is negative. So if I sign a longer contract, I actually see, if I held constant the value, that shirk value actually starts to go down, or player's performance actually starts to get closer to its expected level. Right? Now, the explanations that kind of the authors give here is the idea that, they're being rewarded with a long contract, but right, if you're holding constant the value, the longer the contract, maybe I want to make sure that I'm kind of setting myself up. I'm here for a longer time. And so maybe I want to reward that team that gave me that security, right? So the length here, maybe players are motivated by a longer contract to perform better because they're thankful for the security, while as just the income effect that exists from having a larger valued contract, well, that's going to start shifting the supply curve, and we actually see that the difference between expected and actual performance grow. And that's kind of held up if instead of like forcing it to be linear, like every year counts the same, every contract, every year added to the contract counts the same, to breaking it up into these categories. And it gets a little more interesting there, where you can kind of see what's really driving that effect is these smaller contracts, 2, 3. I mean, the 3-year contract is significant, but the estimate's a little bit smaller. So we've got kind of some insignificant effects coming from 2, 4, and 5-year contracts. But once you get to some of these really long contracts, that's where you see players like really decreasing the shirk value. So really wanting to like reward the team that signed into that long contract. And we see a similar thing for pitchers over here, right? So that look at pitchers, negative coefficient on the length, positive on the value. Once again, if we break it up, the longer contracts are really the ones that are having these huge impacts on decreasing that shirk performance, right? Or getting players to put in more effort. All right. And then they did some stuff with the OPS. I don't think OPS, the whole reason that WAR exists is it's a better statistic. And so they didn't find anything significant here, which isn't that unexpected because it doesn't capture a lot of the other things that are involved. Any questions at this point? Okay. Oh, so that's the paper I wanted to go over. I do believe I have it pulled up here. So Kevin Sturrow. So I don't think there was anything interesting else interesting in this paper. Oh, yeah, there was. I'm lying to you. Here we go. So the next regression that they ran was they basically just looked at performance, and then they created these indicator variables, which was, maybe it's, the year pre and post signing that contract, maybe there's some different effects, right? So before I sign the contract, maybe I'm performing even better than I usually do because I really want to guarantee a long-term contract, okay? And then maybe the year after I sign that deal, right, maybe I kind of slack off a little bit. I get to feel a little bit comfortable. So they created this post variable, which was a 1 if it was the year after signing a contract, and then pre if it was the year prior to them needing to sign. Excuse me. It was a 1 in the year if it was prior to the year in which their contract was going to be up, right? This is the last year of their contract. So this is like they're playing for kind of a big contract here. So, they don't list all of the different control variables. They try to control for what we've got: year, team, positions, the players play dummies, the number of games they play. Got a bunch of different control variables. So we're trying to compare apples to apples here. Now, the composite rating was supposed to kind of capture all these different performance measures of an NBA player. Right? So this Sturrow, he did the one in the MLB, and then he's doing the one with the NBA now as well. Okay. So we've got this pre-indicator variable. So a 1 unit increase in that is going from 0 to 1. So not being in a year prior to your contract being over to being in a year right before your contract's over. And you see that the composite rating that captures all performance of players, there's a significant positive effect. Being in that year prior to your contract being up, we see that players on average perform better. Right? And then if we look at the post variable, we see the exact opposite. In the year following them signing a big or not even a big contract, just a contract, we actually see a reduction in their performance. And that's even controlling for their age, right? You can kind of see here, as players get older, 1 year older, we would see this composite rating of performance decrease. And we really see this kind of hold up for most of the different metrics. So the post variable starts to become insignificant occasionally, but this pre variable, which is that in that year, when your contract's about to be up, players on average score more points, get more rebounds, higher number of assists, block shot. Every metric we see that they have this kind of increase in performance. Okay. Any questions on this? So this is always like a good way to approach questions is if you think that something is going to have an impact, in this case, the year that your contract is about to be up, you just include an indicator variable for that, right? So this was just a 1, it was a year that the contract was about to run up, 0 if not. Now, the way we could interpret this coefficient is if it's a 1, if it is in the year prior to the contract being up, here's the expected or predicted increase in that player's composite rating and their points scored. So like each one of these columns was a different regression. And each column kind of gives us what that regression's dependent or Y variable was. Okay. Any questions on this? I thought I saw one. Okay. I know they have another table in here that's kind of interesting. They then try to do a couple other things where they add in more controls, and they still kind of find that, there's this significant effect in that year, last year of the contract. Well, that post year, you can kind of see here that significant goes away, but it is always negative, right? So this is one thing I want to point out. So they don't have the p-values here, but when you run a regression in Excel, it kind of gives you that p-value. So let's say, and hopefully when I can't remember regressions I'm going to run if there's any p-values like this. So I'm just going to make one up so that we make sure we cover it. So let's say that we've got like, here's our performance. And we had that pre-variable and we had a bunch of other stuff as well, right? So I get my regression output in Excel and it usually tells me, what that coefficient was on the pre-variable. And then it gives me, I think it's the test stat or standard error, I forget the order. And then it usually has a column, it's the p-value. Okay. If that p-value, let's say it was like 0.13, okay? Well, we can only reject the null, or said differently, we can only say that there's a significant effect if our p-value is less than alpha, okay? So the alphas that we compare it to, we have kind of the 1, 5, and 10% significance level, which alpha is just the decimal form of that. So 0.01, 0.05, and 0.10. So if we see a p-value that's less than any of these, we could say that it's significant at that level. So if it's less than 0.1, it's significant at the 10% level. Less than 0.05, significant at the 5% level. Less than 0.01, significant at the 1% level. Well, here we have a p-value of 0.13, so it's not significant at any level. So if it's not significant, what we're really saying is it's not significantly different from 0. Okay? Now remember, what we're trying to capture with these coefficient estimates is the relationship between that x variable and that y variable. So the relationship between being in the year prior to your contract being up and your performance. So if I find a p-value of 0.13, I can't say that it's statistically significant or any different from 0. That there is no relationship between those two things. However, right, just because it's 0.13, I mean, that's barely outside the range. So yeah, this is not significant at the 90% level, the 10% significant level, but it's pretty close, right? Now, how close is close? Well, that's why we have thresholds, right? That's why these are set, these benchmark values are set. But just because we find it as just, barely greater than 0.1, that's still good evidence that there's a relationship between these two variables. It's just not kind of very strong evidence or up to our kind of standard benchmarks that we set. Yeah. Oh, so it's only, well, let's look. It's a good question. I'll repeat the question here in a second. Let me make sure there's nothing else in here I want to mention. I think those were the only two tables. Yeah, I think that's all I wanted to look at. We'll just kind of keep it at that. And I posted this up on Canvas if you want to take a look more at the paper. It's pretty interesting results. But I also posted this thing under the class data folder. I think it's just called Powerlifting Small because I had to make it a little bit smaller. And I'm going to be on sheet 2 here. So I had this old data set, and it's got like a bunch of different powerlifting meets and, different players. Yeah, different players, different kind of lifters, their body weight, age, whether or not they were male, raw. There's different divisions. So these kind of identify different types of powerlifting divisions. I then have kind of this measure of what their weight lifted kind of per pound was. It's not a perfect, it takes into consideration other things, not just kind of weight lifted in the person's height, but kind of what like weight class they're in. So this is a little bit varied. A better variable might just be, just for the way that we're going to think about things, is just the per pound. So this is like weight lifted per pound, right? So, this person weighed 123 pounds, so multiply that by 5, and that's the total amount that they lifted. I've also got kind of the 3 different lifts that they do. So what their best squat was. Oh, this is not in pounds. I lied. This is all in kilograms. So here's your kind of best squat in kilograms, best bench in kilograms, best deadlift in kilograms, and then the total weight lifted, which was just the sum of these three. So let's say I go to run a regression. So I would go to data analysis, go down to my regression, I hit OK. And maybe I'm interested in something like, I don't know, how is the total weight lifted? So actually, yeah, we'll do total weight lifted. Go back up to the top. How is that impacted by things like what the person's body weight was, their age, what gender they were, and kind of the divisions they were in? And we could even include, well, we won't do age squared. I'll make it a little bit complicated for this class. So I then control shift or command shift on a Mac, hit the down arrow, and it'll select all of my data for me. So that makes it a lot easier when you have these big data sets with like 86,000 observations. I selected the labels at the top of the columns. And this is an important thing. So I've had a couple people like asking me and reaching out to me and sending me the regression results. If you don't select so first of all, you have to click this button, but if you don't select the labels as part of your range, so actually I'm gonna not do it and show you what happens. So let's say I would have started it on the second row, which is where the first data point is, but I don't include the values. So I don't have I don't include the labels. So I don't have my labels anymore. Hit OK. It'll run this regression for me, but like, I have to remember the order because it's just telling me this is X variable 1, 2, 3, 4, 5. If I go back and do the same thing, but instead of starting at that second row, I start at the first one like I originally had, I kind of started to show you, where I selected my labels. Now when I run this, it attaches those variable names to the regression, okay? Or regression output, I should say. So I'm looking at this output. It tells me the coefficient on each one of these variables. So essentially, this is like, I'll write this out for us. So if I was thinking about what I did here was, I kind of went on total weight lifted was a function of, the first thing was body weight. The second thing was age, all these other variables. So the output I see, here are my coefficients, right? It's my first column. To determine whether or not they're significant, well, notice here, I get all 0 p-values. So I knew these things mattered ahead of time. So when I include, I know that they're going to have a strong and significant effect. So these p-values aren't actually 0. They're just so close to 0 that Excel isn't going to display them out to any other value. So I think if I go here, let me see. These one might just be so close to 0 that even if I format them, let's do scientific. Yeah, they're still all 0. Right? What's something I could include here so I can give you an example of what happens if they're not 0? Because that's what I need. Let's see, on this original data sheet, did I have anything else that wouldn't matter? So the problem is here, this was the one I didn't clean. Let's do, okay, let's do another regression here. I'm just gonna move this. Maybe if I just include the Wilks, it'll give us an example of something. So I'm going to try to include all the Wilks score and see what I get, although this isn't really technically what I should be doing, but here we go. So now I've got some p-values. Now you can kind of see, even if they're really small, right? E to the negative 35 means move that decimal point 35 places to the left. So here we've still got p-values that are almost all 0, right? Or at least really close to 0. And that's because we only really included things that we think should impact it, right? Like if I would have included something like, I don't know, eye color, right? And had it be a 1 or 0, that shouldn't have any impact on weight lifted. We should have ended up with a p-value that's like close to 1, right? It's really, really high. But I didn't have that information here. But this is this other column you want to focus on. This is where your p-value should be. And so which ones should I focus on? Well, it depends on what the question of the paper was. Maybe the question that I had was, does gender actually influence kind of the weight lifted by these individuals? Well,
I found a p-value of 0. It's going to be less than all my alpha. So yeah, there's a strong significant effect of gender here on weight lifted, right? That would be something like that. So I don't have to like mention every single variable, just the variables that were of interest to my specific question. Does that answer what you're saying? Yeah. Any other questions on kind of this output or how I use this output? So it always puts these confidence intervals over here. For the sake of what we're doing, we don't really have to worry about these. So if you run a regression and want to put it in that project, you could delete these and just kind of put this in there. The coefficients and that p-value are the main thing that we want to see. Okay. What else did I want to say here? Let me think if I thought there was something else I could do here. Oh, I know what it was. So here's a bunch of our different regressions. So I'm going to go back to sheet 2. Just kind of a trick. If you're down at the bottom, if you hold Control Shift and hit the up arrow, it'll send you to the top. So maybe I'm looking at this and I say, okay, let's go back to data. I think I want to, instead of using the total weight lifted, maybe I am thinking about this per pound of body weight. Right? So I have to have, maybe I want this as my Y variable. And then because it's already like capturing body weight, I'm just going to look at the impact of these things here. So I go to regression, select per pound, go back up, the X variables I want, just age through wraps, right? Control Shift, Command Shift, the Mac arrow. Sorry, on a Mac, hit the down arrow. Got my labels selected. So now when I look at this output, once again, the p-values are all pretty close to 0. So everything looks like it has a significant effect. But you can kind of notice like the size of that effect, from being male is relatively small, right? So on average, you'll lift about, the male, if you could hold these other things constant, would lift about 1.5 kind of more kilograms per kilogram, right? Per body weight or per kilograms of body weight. Right? Now, there's a lot of more interesting things we could do here if we didn't have the limited data. So I've worked with this a little bit. It's got a lot more information, but I had to clean some of it up because, there's missing values. And here we've got some 140 plus. Excel can't run a regression if you have a non-numerical value in there. But, you could play around with this, this data and really, do a bunch of different regressions. And so this is how we would kind of use that output, right, to answer that question. Or maybe you're really concerned about kind of age, right? And you can see that as someone gets older, like they're lifting kind of less than these powerlifting meets. Okay. Any other questions? Anything I've done here? How maybe you would apply it to your project if you have questions on that? Okay. Another thing I wanted to mention, because this could be helpful to some of you with your projects, but also something that we just want to understand about this regression output. So let's go, where was the one where I was running? So it probably would have been sheet 3 was the, no. Yeah, okay, so this was the one that I ran. So our Y variable here was, excuse me, total weight lifted. Kind of we have the individual's body weight here. Right? So maybe I'm saying something like, okay, the interpretation of this coefficient is if the X variable goes up by 1 unit. Well, when I have a variable like body weight, going up by 1 unit of body weight should increase the expected total weight lifted by 3.12 kilograms. That's how we would interpret that, right? A 1 unit change in the X variable causes a 3.12 here predicted increase in the Y variable or total weight lifted. So what if I wanted to know the effect of, or what if I was trying to say, okay, if somebody gains 10 additional kilograms, what's the impact of that on their weight lifted? Right? That's kind of my idea. Well, if I know the effect of 1 additional kilogram, all I would have to do is multiply that by 10. Right? Here's the effect of 1 additional kilogram. So if I want the effect of 10, just multiply it by 10. Right? Because, sometimes the units, it might be like $1 increase. Well, a $1 increase in, maybe expenditures or something for a professional sports team is nothing. It has an impact, right? But they're, practically not spending $1 more. They're practically probably going to spend an additional $1 million, right? So you can get the effect of $1 and then multiply it by 1,000,000 to get the effect of $1 million. Same kind of idea here, right? Get the effect of 10 kilograms, multiply that coefficient by 10. Okay. Now for these other variables, like this one was, so the raw is just kind of a 1-0 variable, right? So it was a type of division in powerlifting where they aren't allowed to use certain gear. And so you can see when they're not allowed to use certain gear, like they've got, wrist straps, knee wraps, I forget, actually you can use wrist straps here. I forget what the other one is, but you can't use knee wraps. And so the impact of if you're lifting in that division, well, here a 1 unit increase is just going from a 0 to 1. So if I'm lifting in this raw division relative to not lifting in it, the expected amount of weight I lift is 134 kilograms lower, right? And that's how, those 1-0 variables are a little bit easier to interpret, right? Any questions on this? I'm trying to think of other things that would help some of you. I don't think a lot of people need this for their project because they're not going to be running multiple regressions, but a couple of you I know, sometimes I've mentioned, well, you could look at 2 different dependent variables, right? Or maybe you want to use, different types of independent variables. So one thing that's kind of interesting, so if I look at this and I say, all right, I'm interested in the impact of gender on total weight lifted. So I'm going to look at this total kilograms lifted. I'm then going to look at just this male variable, right? Select that. So I've only got one kind of independent variable or right-hand side variable there. I look at that coefficient and I see if the lifter is male versus female, they lift on average 275 kilograms more. Well, this seems absurd, right? And it's very significant. Well, that's because I'm not accounting for or controlling for a lot of other factors, right? So if I go back to this sheet and I instead say, okay, well, look, one main difference I know that exists between males and kind of females is a different average kind of body weight and height, right? So, not zoom. So I'm going to go to data analysis here, get into my regression tool. I'm going to keep the Y variable the same, but now I'm just going to say, okay, well, if I include body weight and age, what happens to that coefficient on male, right? So I'm going to select those 3 variables. Now when I look at the output, well, that effect on kind of that male variable has fallen from 275 all the way to 193, right? And if I don't account for the fact that maybe more males tend to be in these divisions that use more, what's it called, like gear or performance enhancing, kind of like I said, knee wraps, things like that. But when I included all of the variables, right, notice it fell from 193, fell a little bit more down to 189. And if I could, if I had a height variable and I add that in and I, have all these different things that likely influence the amount of weight lifted, I'm probably going to see that male variable starts to get closer and closer to 0, right? If I can account for all these other factors, right, the gender doesn't seem to play as large of a role, okay? Any questions on that? Okay. Well, let's see if there's anything. Oh, the other thing just to mention, I think I've mentioned this before, but I just want to make sure that I kind of going over things a lot more in Excel and with linear regression here towards the end. So let's say, I don't know, we had something annoying like, let's say I wanted to look at, let's say I want to include only body weight and not age, right? So I want to keep my Y variable to be this total weight lifted, but I only want to include the 2 kind of right-hand side or independent variables. Now, why would I want to do this and not use all the data I have? It would be dumb to do this, but let's just say I wanted to so I can show you something, because some of the data I sent you guys has extra variables you might not need. So you go to data analysis and you go to regression here. We got the same Y variable, but I only want body weight. I'm going to hold shift, not shift, hold control and select male. So it might look like I'm selecting both of these columns, and it looks like I could try to select both columns in here. when I go to run this, it's going to give me this contiguous reference, right? So I think if I go in here, I can type it in. So C, what, 86381, 86381. So even if I type that in there, it's still going to give me the error. So even if I can get these two columns typed in here correctly, it doesn't work, right? So it's a limitation of Excel. So what I need to do is have those variables next to each other. So the easiest way to do this is right-click, insert a column, move the variables over next to each other that I want to use, delete this column. Now when I go to my data analysis and select my X variables, they'll be right next to each other. And this runs no problem, okay? So we gotta make sure our variables are next to each other when we're doing this regression analysis or trying to perform this regression. Okay. So that was one thing I wanted to make sure I mentioned. Any other questions over anything with Excel? If some of you have kind of started playing around, any issues that you've had? Okay. I think that should kind of cover it for me. I don't know if there's anything else I really want to say here that's too interesting. Yeah, I think this should kind of cover it for us. So we got a little bit of kind of finished off some topics related to college sports, look at a couple papers, started to think about the regressions they're using. And one thing, you know, I think I mentioned this as well in prior class, but if we're looking at, oh, I already closed it out. But if we're looking at these papers, you should have something in your project that looks similar to this, right? Like typing out or writing out what your regression equation would look like. And you don't have to include every single control variable or every, you know, you could even just kind of write out the most simplest regression where I have a Y variable and I want to know the relationship between that and some other variable that I think impacts it, right? So just kind of writing out a small linear regression equation that looks similar to what you did in Excel. That should be somewhere in your data section, or it could be in your analysis section. Either one, I'm not going to, it kind of varies if you look at papers, but as long as it's somewhere in that data or data analysis section, that's good, but you should have one of those. Yeah. This? Oh, you mean like in Word? If you want to just use B's, that's fine. That's probably the easiest way. That's why I usually use B's, because like to do this in Word, you got to insert a symbol and it just becomes kind of, you know, do this subscript. You can kind of write like B1. You don't have to like make it look as pretty as some of the papers we've looked at. So you could have just went, let me type one below it here. So like equals B1 plus B2 times, so you could just type it out like that. Yep. All right, as promised, a little bit short of a class today. I probably will post an online quiz after class that'll be due before we meet on Tuesday, okay? All right. All right, well, I will see you guys Tuesday. Enjoy your weekend.